Hey guys, I welcome you to my YouTube channel. My name is IBM, and today I've decided to solve Physics 0625 Paper 3. This is February March series. This is a theory core paper. One student has been putting me on pressure to solve this paper. So the question paper is in the video description. You can download it if you want and follow the videos. For those who are always asking for the mark scheme, even when the questions have been solved in the videos, you can always wait for the exams to be released next month for you to see the mark scheme and maybe compare with what I have solved. Otherwise, I trust that I have tried my level best to give correct solutions to these question papers. So without wasting time, I would like to take you to the question paper. So this is the question paper, which is paper 3. It is called Theory Core. It is February March 2024. The paper is supposed to be 1 hour and 15 minutes. I may try to keep time. This is a very easy question paper. The only instruction I want to talk about is the last instruction, which says take a weight of 1 kilogram to be 9.8 newtons, which means you are going to be taking G as 9.8 as opposed to 10, which most of you might be used to. Even teachers from the old curriculum, if you have not been very careful with the changes in the curriculum, you might have been giving your students 10. But effective this year, it is students are going to use 9.8 meters per second squared as G on Earth. Then the paper is 80 marks, so let's just start with question number 1. The figure 1.1 shows the distance time graph for a student. The student walks out of a classroom, stops to talk to some friends, and then walks to their exact next class. So walks out of the classroom, that is A to B, stops, that is B to C, then continues to the next class, that is C to D. Describe the motion of the student between time equals to 0 and time equals 6 seconds. So in the first point, you see it is a straight line. And remember, the gradient of a speed of a distance time graph is the speed. And a straight line means the speed is constant or the acceleration is 0. So we can say between 0 and 6 seconds, the student is walking with a constant, steady, uniform speed or 0 acceleration. So I will simply say walking with a constant. I can use a steady to mean constant. I can use uniform to mean constant. Because this is a distance time graph, I will say speed instead of velocity. But remember, constant speed, uniform speed, constant steady speed, because it's a straight line, it means 0 acceleration. So you can say the student is working with the 0 acceleration. Or I can say 0 acceleration instead of, when the speed is constant, the acceleration is 0. Then calculate the speed of the student between time t equals to 0 and time t equals 6. Of course, the speed is the gradient. The speed is going to be the gradient, so I'll simply say speed from a distance time graph, speed is equal to the gradient. So I'll get the change in the y values is 12 minus 0. The change in the x values is going to be 6 minus 0. So this is 12 minus 0 divided by 6 minus 0, which I think gives us 2 meters per second. Unlike the triple science class, those doing extended, for the course, most of the questions will have units. But for the extended, most of the questions we may not have units, so you must be very careful with the units and you should write the correct units. Determine the length of time for which the student stops walking. So student stops walking at 6 seconds and again starts walking at C, which is, I think this is 11. So between 6 and 11 seconds, the student has stopped walking. So the length is going to be 11 minus 6, which gives us 5. So the answer is going to be 5.0 or simply 5 seconds. Then compare the student's speed in section AB with the speed in section CD. So when we compare the gradient of AB and the gradient of CD, we notice that CD is very close to the horizontal than AB. In other words, AB is actually steeper than CD. That means the speed along AB is higher than the speed along CD. So I'll say more faster in AB. The speed is more faster in AB. Or if you want to be very specific, you can check the speed. You can find a gradient here. The gradient here is approximately, this is, what is this value here? 12, 1, 2, 3, 4, 5. This is 13, 13.2.4, 13.5, 14. Let me check. The scale is 4 divided by 10. That is 0.4. So this is 13.4.8. Then this is 13.8 plus 0.4, that is 14.2. So the gradient there will be 14.2 minus 12 divided by 14 minus 11, which is 3. So that is going to be 2.2 divided by 3. 2.2 divided by 3. And yet this was 12 divided by 6. So it's like, is it twice? Let me check. 1, 2, 3, 4, 5. No, this is 14, not 13. Then 14.4, 14.8, then 15 point. This is 15.2, not 14. So that is 15.2, which gives us 3.2 divided by 3. And this is 12 divided by 6. So let's check. 3.2 divided by 3 is 1.0, approximately 1. So it's like this gradient is approximately 1.0, yet this gradient was approximately 2.0. So it's like this gradient is twice the other one. So you could, if you were good at this, you could specifically say the speed. This is another alternative. Speed in section AB is twice or is double speed in section CD. As simple as that. But this is enough because the line is steeper. It is moving faster in AB because the line is steeper along AB. You can check that line. A student determines the volume of a piece of metal. The student pours 30 centimeters cubed of water into the measuring cylinder. The piece of metal is submerged in the water, and the new volume reading on the measuring cylinder is 42 centimeters cubed. So the student's first pours, and the reading is 30. Then now it is 42. Capture the volume of the piece. So the volume is going to be just the change in that. So it is going to be 42 minus 30, which is automatically 12 centimeters cubed. Then the mass of another piece of metal is 320 grams. The volume of the piece of metal is 40 centimeters cubed. Calculate the density. So density, you can use rho for density, or you can use D for density. I prefer to use rho. Density is mass divided by volume. Because these are 4 marks, make sure you write every step. Then the mass is 320 in grams divided by the volume, which is 40 centimeters cubed. Then you press your calculator. 320 divided by 40. So this is giving me 8. but it is grams divided by centimeters cubed. So it is grams per centimeters cubed. So this is going to be 8. The units are going to be grams per centimeters cubed. Alternatively, we know that 1 gram per centimeters cubed is the same as 1000 kilograms per meters cubed. So another answer could be 8,000. The units could be kilograms per meters cubed. So this could be another answer. Instead, if you want your answer to be in kilograms per meters cubed. The student drops the piece of metal into a tank of water. 2 vertical forces act on the piece of metal as it falls through the water in the tank. So it is moving. So one of the force which acts vertically downwards is the weight of the piece of metal. So this is going to be the weight. Because it is moving, there is friction which acts in the opposite direction. This is going to be either friction, or you can call it the drag. If you want to be specific, you can say viscous drag, because friction in the fluids is called viscous drag. Then complete the diagram in the figure by labeling the two forces. So I said it is friction or drag, or you can say viscous drag. The upward force is the same size as the downward force. That means the friction is equal to the weight. Describe the motion of the piece of metal as it falls through the water. If the forces are equal but opposite, then it means the resultant force is equal to 0. The acceleration is going to be 0. The speed is going to be constant. So it means the piece of metal moves with a constant speed. So falling with constant, or you can use steady or uniform speed. The reason, because the resultant force, since the resultant force is 0. So whenever a body is moving whenever a body has no resultant force, it moves with a constant speed. So because the upward force is equal to the downward force, the resultant force is 0, so the speed is constant. The figure shows a computer on the surface of a desk. The weight of the computer is 48 newtons. The area of the computer in contact with the surface is 20 centimeters cubed. Actually, the pressure. So we know that pressure is equal to the force over the cross-sectional area. The force is 48 in newtons. The area is 20 in centimeters cubed. So 48 divided by 20. So this gives me 2.4. So they want the answer in newtons per centimeter squared. So it is 2.4 newtons per centimeter squared. A student uses a force of 12 newtons to tilt the computer as shown. Okay, so the perpendicular distance from the pivot is 32. The horizontal force is, so this force is acting at 90 degrees to 32. Calculate the moment of the 12 Newton force about the pivot. So by definition, moment is equal to the product of the force and perpendicular distance from the pivot. Force times perpendicular distance from the pivot. These are 3 marks, so you have to write the formula. The force is 12 newtons times the perpendicular distance, which is 32 centimeters. So the moment is 12 times 32. So this is giving me 384 newtons centimeters. The figure shows a student using a battery-powered device. State the energy store in the battery. So the energy store in the battery, that is, in the battery we have chemicals. So this is chemical potential energy, or simply chemical energy. So I'll say chemical potential energy. The student pushes the device along the floor at a constant speed. That means the resultant force is 0, with a horizontal force of 14 newtons. The student pushes the device for a distance of 4.5 meters. Calculate the mechanical work done. So we know that work done is the same as the force times distance moved in the direction of the force. Force times distance moved in the direction of the force. So the force is 14 newtons and the distance moved is 4.5 in meters. So I'll just press my calculator. 14 times 4.5. So that is 63 joules. So this is 63 Newton meters, which is the same as joules. The student uses the device for a time of 30 seconds. The energy input to the device is 5,400 joules. Calculate the power input to the device. So power input, of course, is going to be the energy input. Power is energy over time, so it's energy input divided by the time taken. So the energy input is 5,400 joules divided by the time, which is 30 seconds. So 5,400 divided by 30 seconds, that is 180. So the power is 180 watts. The figure shows a metal container used for storing petrol. There is some petrol gas above the liquid petrol inside the metal container. Okay, outside of the tank is a shiny white surface. Describe the arrangement and the motion of particles in the liquid petrol stored in the container. Arrangement and motion. How are the particles in a liquid arranged in general? And how is their motion? So for liquids, we know that particles are randomly arranged and they are slightly further apart compared to those in solids. That's number one. So I'll say particles, that is for arrangement. Particles are randomly arranged and slightly further apart than in solids. So for liquids, we know that particles are randomly arranged. The arrangement is irregular. They are randomly arranged and they are slightly further apart than in solids. Then when we talk about motion, the particles move randomly around, colliding with each other and with the walls of the container. The particles move randomly around, colliding with each other and with the walls of the container. Okay, so that is the movement. When it comes to motion, the particles move randomly free around, colliding with each other and with the walls of the container. When it comes to arrangement, they have an irregular pattern and they are slightly further apart than in solids. Then the temperature of the gas, the petrol gas inside the container increases. Temperature of the gas inside the container increases. Set and explain any change in the pressure of the petrol gas on the metal container. Note that the temperature has increased. Of course, if temperature increases, the pressure increases. So number one, I will simply say pressure increases. Pressure is directly proportional to temperature if the volume remains constant. So pressure increases. And why does it increase? Of course, the particles, because the temperature increases, the particles gain more kinetic energy. The particles gain more kinetic energy and move faster. The particles gain more kinetic energy and move faster. What is the effect? If they move faster, it means there will be more frequent collisions with the walls of the container. So this is leading to more frequent collisions with the walls of the container, leading to more frequent collisions, that is many collisions with the walls of the container in a short period of time, resulting into harder collisions with the walls of the container, leading to more frequent collisions with the walls of the container, resulting into harder collisions with the walls, resulting into harder collisions with the walls, hence greater pressure. Hence greater pressure. Okay, that is the effect of temperature on the pressure of a gas. Then describe how thermal energy travels from the sun to the petrol inside the metal container. So it is coming from the sun, it goes through the metal container, then it goes through the liquid. So from the sun to the container, between the sun and the container, we have infrared radiation. Then in the container, in the metal container, we have conduction. And of course, through the liquid, we could have convection, but I don't think it is necessary. They didn't mention the liquid. It is from the sun to the petrol inside the metal container. So I will say infrared radiation, that is from the sun. Infrared radiation. Infrared radiation through space. And maybe atmosphere. Then now conduction through the metal. Then conduction through the metal. So it starts as infrared radiation from the sun, it passes through space and the atmosphere, and then it is conducted through the metal. So in space it is infrared radiation, that is electromagnetic waves, and then in the metal it is the process conduction. So these are the two processes we are considering. In space it is infrared radiation, then in the metal it is conduction. The figure represents a transverse wave. So we have been given a displacement against time graph for transverse wave. Determine the amplitude of the wave in the figure. So amplitude is the maximum displacement. So if this is the equilibrium position, maximum displacement is this distance here, or it can be this one here, and that distance is 30. So the maximum displacement, which is the amplitude, is 30 millimeters. Then determine the frequency of the wave. So we know that frequency equals to the number of waves per second. The number of waves per second. So if you look at for 1 second, here we have two waves in 0.20 seconds. So we want the number of waves in 1 second, so I will divide 2 by 0.2. So it means the frequency is going to be, there are 2 waves in 0.2 seconds. So this gives us 10 waves in 1 second. So this is 10 waves per second, which is the same as 10 hertz. So the frequency is going to be 10 hertz. We expect 10 cycles in 1 second, so this is 10 hertz. Alternatively, you can use the formula. You can say frequency is 1 over the period. So just look for the period. The period is the time for 1 cycle. If 1 cycle starts from here, the next time I come back to this point, that is 1 cycle. So 1 cycle is 0.10 seconds. So the frequency is going to be 1 divided by the time for 1 cycle, which is 0.10, which still gives us 10 hertz. State the name of one type of transverse wave. Now, there are so many types of transverse waves, but they are all, I can mention electromagnetic. You can mention any electromagnetic wave. For example, you can mention radio waves, microwaves, infrared, X-rays, gamma rays. Those are electromagnetic waves. In addition, you can mention seismic S waves. Those are secondary waves. Seismic S is standing for secondary waves. You can mention waves on the surface of water, waves on the surface of water. Remember, I mentioned electromagnetic waves. Electromagnetic waves. When I mention electromagnetic waves, I mention radio waves, infrared. You just pick one. Microwaves, visible light or just light. You can mention ultraviolet light. You can mention X-rays. You can mention gamma rays. All these ones are transverse waves. So you can mention any of these electromagnetic waves, or you mention seismic S waves. You can mention waves on the surface of water, any of those. So I'll add it here light, because when I just mention electromagnetic waves, people will not understand. But light is an electromagnetic wave, so I just mentioned one of them as light because it's the common one to a core student. Describe the vibrations in a transverse wave. Of course, we know that in a transverse wave, vibrations are perpendicular. Vibrations are perpendicular. Vibrations are perpendicular. Or when I say perpendicular, it means at right angles. To the direction of propagation of energy. If it was longitudinal, for longitudinal it is just the opposite. For longitudinal waves, the vibrations would be parallel to the direction of propagation of the energy. For transverse, vibrations are perpendicular to the direction of propagation of the energy. Then the figure represents an object placed close to a thin converging lens. It is converging. The scale for the grid is shown. So one box is 5 centimeters in the horizontal and in the vertical. Determine the focal length of the converging lens. Use the information in the figure 7.1. So let's check the focal length. So for the focal length, a ray parallel to the principal axis converges to the principal focus. So the focal length is the distance from the principal focus to the center of the lens. A ray parallel to the principal axis converges to the principal focus. So the focal length is going to be the distance from the principal focus to the center of the lens. So this distance here is going to be the focal length. Let me write it at the top. This is the focal length. I'm calling it F. And the focal length, we are seeing there are two boxes. There are two boxes. Remember, each box is 5 centimeters. So because there are two boxes, the focal length is going to be 2 times 5. So F is going to be 2 boxes times the value of each box, which is 5 centimeters, which gives us 10. On the figure, draw the position of the image formed by the lens by continuing the path of each ray beyond the lens. Use an arrow to indicate the position of the image. So I have drawn one ray which converges. Of course, you can use a perfect ruler. Then I'll also draw a ray which goes through the principal focus, the optical center. This ray cannot be deviated. So this ray just continues on its way. Okay, so that ray just continues on its way. So it means it's like if I was to draw this on a question paper, I'm very certain the object, the image is most likely going to be at this point here. Let me try to be accurate and see. It's not very easy to draw on a computer. Somebody should recommend an application for set instruments that I can use on the ruler. Okay, so those are the rays. They are meeting there. So this is going to be a real image. So I will try to increase, I'll just try to make this thicker. I don't need to draw exactly what the examiner drew to be wasting my time. So that is going to be my image. So use an arrow to indicate the position of the image. So I have used an arrow here to indicate the position of the image. So the rays just continue without, this one goes without deviation. This deviates through the principal focus or the focal point. The figure shows the regions of the electromagnetic spectrum. In the figure, one region is unlabeled. State the name of the unlabeled region. So they are starting from radio waves. So Reed's mother is visiting Uncle Xavier's garden. These are the electromagnetic waves, starting from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. So what is missing is actually X-rays. Reed's mother, Reed's mother is visiting Uncle Xavier's garden. So that is their order. In the figure 7.1, region is unlabeled. We have labeled that. Say the name of the unlabeled region. So it is X-rays. Describe one use of ultraviolet. Ultraviolet is now nowadays very common. So we know that ultraviolet is used for security marking. Security marking normally uses ultraviolet. Detecting fake banknotes. Detecting fake banknotes. Detecting fingerprints. Uses ultraviolet. Sterilizing food and water. Sometimes they use ultraviolet sterilizing food and water, food or water. By the way, one use could be negative, for example, causing skin cancer. It could be a negative use, skin cancer, but that is negative. Describe one harmful effect on people due to excessive exposure to ultraviolet. Of course, still I can bring in skin burns. So it damage to surface cells or skin, or it damages the eyes, causing what we call cataracts. So I can say damage to surface cells, the skin, damages the eyes. When I say damages surface cells, you can say causes skin burns. Skin burns. You can say mutation of cells because it damages cells. You can say mutation of cells. It could lead to cancer, skin cancer leading to cancer. You can talk about, instead of saying a damage to surface cells, skin, damages to eyes, you can talk about eye conditions such as cataracts. Causes eye conditions such as cataracts. The condition where you feel like you have a fog on your eye lens, that is cataracts. That eye condition could be as a result of ultraviolet, exposing your eyes to excessive exposure to ultraviolet rays. The figure shows a permanent bar magnet. It is a permanent bar magnet. Describe an experiment to identify the pattern and directions of the magnetic field lines around the bar magnet. You may draw on the figure as part of your answer. So as part of my answer, I may draw field lines. I know that field lines originate from north and they terminate to the south. So I'll draw arrows from north to south. Okay, so I'll just put this in writing. The only way I can tell the direction of the arrows is by using a plotting compass. I can put a number or several plotting compasses around the bar magnet, and then I look at the direction in which they point. That will be the direction of the magnetic field. The compasses are going to be aligned. So one method, I would say, place a number of plotting compasses around the magnet. Place a number, that is many. Place a number of plotting compasses, around the magnet. The arrows of the compasses line up. They line up to show the direction or to show the pattern. To show the pattern and the direction of the arrows give the direction of the field lines. If you want, you can put plotting compasses here, but it will cost you a lot of time to draw those compasses. But place a number of plotting compasses around the bar magnet. Then you will see that the arrows of the compasses tend to line up to show the pattern. And the direction of the arrows gives the direction of the field lines. Alternatively, where will I write the second method? Let me write the alternative here. Alternative method, I'll write it here. Place a card on the magnet. Place a card on the magnet. I'm now going to use iron filings and sprinkle iron filings on the card. The next thing, you gently tap the card. Gently tap or shake the card. Gently tap or shake the card. The iron filings are going to arrange themselves. Iron filings arrange themselves to show the pattern of the magnetic field. But of course, they may not show you, they just show you the pattern of the magnetic field lines, but not the direction. So you will still need a compass. So use a compass to get the direction of the field lines. You would see the pattern by tapping the card. The iron filings arrange themselves in a certain pattern to show the magnetic field lines, but you don't know the direction of the magnetic field itself. So you use a plotting compass to see where the pointer points. That is the direction of the magnetic field. Okay, so I think that is the only technical question in this paper. State the name of the material that is suitable for a permanent magnet. A permanent magnet should be able to retain its magnetism, and this is normally steel. Steel is the one which is used for a permanent magnet, but we have what we call a neodymium. Neodymium. This material keeps its magnetism for a very long period of time. Then state one use of a permanent magnet. Of course, permanent magnets can be used in electric motors. Most of the electric motors you have seen, they have permanent magnets. Loudspeakers have permanent magnets. Loudspeakers. Many burglar alarms. And so many others, they have permanent magnets. Okay, so this was steel, not iron. Iron gives a temporary magnet. A student connects the electrical circuit shown in the figure. So this is the circuit. I think this is a series circuit: thermistor, lamp, ammeter, switch, battery. The figure shows part of the circuit diagram for the circuit in the figure 9.1. Complete the circuit diagram to represent the circuit. Use standard electric symbols. So they have drawn for us the battery. So we need to put the thermistor. So I'll add the thermistor here. The symbol for a thermistor is simply this. Then we have the lamp. The symbol for the lamp is this one here. Then we have the ammeter. The symbol for the ammeter is this one here. And I think that is all. The switch has already been drawn, so I just complete the circuit. As simple as that. Those are 4 free marks. Then the potential difference across the lamp is 5.4 volts. The current in the lamp is 0.2 amperes. Calculate the resistance of the lamp. Okay, so we know that resistance is equal to V divided by I. So this is divide 5.4 divided by 0.2. 5.4 divided by 0.2, which is 27. So the answer is going to be 27 ohms. The lamp is switched on for 30 seconds. Calculate the energy transferred in the lamp during this time. So we know that power is equal to energy divided by time. So it means that energy is going to be power times time. But power also is equal to current times V. So it means energy is going to be I times V times T. So I'll just substitute here. The current is 0.2, V is 5.4, that is the power. Then the time is 30 seconds. I think this is the simplest method. So we have 5.4 times 0.2 times 30. So this is 32.4 or approximately 32. Approximately 32 joules. The student increases the temperature of the thermistor. Temperature increases. State and explain what happens to the current in the circuit. If temperature increases, resistance of a thermistor decreases because resistance is inversely proportional to temperature for a thermistor. If temperature increases, resistance of a thermistor decreases. And if resistance is equal to V over I. If resistance decreases, then more current flows. So the current increases. Current increases. The reason, I'll say because resistance of a thermistor decreases when temperature increases. The resistance decreases when temperature increases for a thermistor. So we call it, when we advance in high school, you call it the negative temperature coefficient. Although I don't encourage any student who has done core physics to do physics in high school. This is, I think, nuclear physics. The figure represents an atom of carbon. Okay. Complete the labels of the particles in the figure 10.1. On each dotted line, write the name of the particle. So inside the nucleus, they have already mentioned the neutron. The only particle which is missing is the proton. So the other one is the proton. Then, of course, around the nucleus, we have the electrons. An atom of lithium has the nuclide notation Li73. Draw a clearly labeled diagram to represent one atom of lithium. So one atom of lithium, so I'll start by drawing the nucleus. Let's have the nucleus. I'll call this the nucleus. It has 3 protons, so I'll say, here they said, here protons were white, neutrons were dark, so I'll use a different notation. Let's say protons. Okay, let me shade the protons. That's 1, that's 2, that's 3. There are 3 protons. Then, of course, lithium has 7 minus 3 neutrons. This is number of neutrons, 7 minus 3, which is equal to 4. So I'll add 4. So those are the neutrons. So I'll call this one the nucleus. The nucleus, I'll call this one the neutron. And I'll call this one the proton. Then, because there are 3 protons, there must be 3 electrons for a neutral atom. So I'll draw one shell outside. And I'll put 1, 2, 3. I'll represent the electrons like this. And I'll call this one the electron. Okay, so that is a simple notation of the lithium nucleus. An isotope of carbon has, of course, there are 3 electrons because normally the number of protons is the same as the number of electrons. That's why, because there are 3 protons, I have to add 3 electrons on the outer shell. An isotope of carbon has a half-life of 5,700 years. A sample of carbon 120 contains 120 milligrams of this isotope. Calculate the time taken for this isotope of carbon to decay from 120 milligrams to 15 milligrams. For those who are just starting, you can do this manually. For half-life, it means you divide by 2. So you start with 120, divide by 2, it becomes 60, divide by 2, it becomes 30, divide this by 2, it becomes 15. So this is 1 half-life. This is 2 half-lives. This is 3 half-lives. Because every time you divide by 2, that is after 1 half-life. So it means the number of half-lives equals to 3. So if I want to find the time for the isotope of carbon to decay into that, it is after 3 half-lives. So this is 500, 5700, another 5700, another 5700 years. So the total is 3 times 5700. That is the time. 3 times 5700. I think that is 17. 3 times 5700. 17100. Okay, that is 17,100. Of course, there's another method, but I don't want to do it for core physics, not at all. Then the last question, the figure represents the 4 planets nearest to the sun, that is space physics. 2 of the planets in the figure are not labeled. On each dotted line, write the name of the planet. Of course, the simplest way to know the order of the planets from the sun, my very easy method just speeds up naming. My very easy method just speeds up naming. That is the order of the planets from the sun, right from, this is Mercury, so this must be Mercury. Next to the sun, Mercury, followed by Venus, Earth, the next is Mars. So this must be Mars, followed by Jupiter, Saturn, Uranus, and Neptune. Then the distance of Venus from the Sun is 1.1 times 10 to the power of 11 meters. The speed of light is 3 times 10 to the power of 80 meters per second. Capture the time it takes light to travel from the Sun to Venus. So we have the speed, the distance, and the speed. So we know that speed is equal to distance divided by time. So the distance is 1 point. Sorry, we want to find the time. Speed is distance over time, so time is distance over speed. So time is going to be the distance over the speed. So that is 1.1 times 10 to the power of 11 divided by 3 times 10 to the power of 8. So I have 1.1 exponent 11 divided by 3 exponent 8, which gives us 366.7. 366.7, or approximately 370 seconds. Then the mass of the Earth is greater than the mass of Venus. The mass of the Earth is greater than the mass of Venus. The gravitational field strength on the surface of the Earth is 9.8. Remember, gravitational field strength also depends on the mass of the object, or the mass of the planet. So it means the gravitational field strength on the Earth is most likely going to be greater than that of Venus. Suggest a value for the gravitational field strength on the surface of Venus. So I am going to give any value less than, let me say, when I look at the masses, it is less, let me say 8.0. So any value, give any value less than 9.8 newtons per kilogram, because G, or gravitational field strength, that is G, also depends on the mass. Because the mass of Venus is smaller, its value of G, or gravitational field strength, is also smaller. Then give a reason. So the reason is very simple. I would say it is proportional to the mass, but Venus has a smaller mass. It is proportional to the mass, but Venus has smaller mass. Alternatively, we could also say it is also inversely proportional to the distance from the Sun, or it is also inversely proportional to, it is actually inversely proportional to the square of distance from the Sun and Venus is closer. G is inversely proportional to the square of the distance from the Sun. Because Venus is closer, its distance is smaller, it means its G is going to be, because Venus is closer, its distance is smaller. When I divide 1 by a smaller value, now let me check here. My very easy method. It's inversely proportional to the distance from it's inversely proportional to the distance from the Sun. So because Venus is closer, then it means G is going to be actually smaller, even if I don't indicate this. Okay, so I think that marks the end of this paper. See you in other papers. I wish you all the best in your forthcoming exams for those who are sitting May, June, the next month. All the best. Until next time, bye bye.